We're being asked to draw some Lewis dot structures of the following. We see carbon dioxide, selenium oxygen difluoride, the nitrite ion, phosphoric acid, sulfite, diphosphorus, tetrahydride. We'll model some of these together, knowing that we can check our work as we talk through. So I'm going to just take this off and give myself plenty of room. I'm going to write large so we can see it on the screen. The first molecule we were being asked to draw was carbon dioxide, CO2. So what I'm going to do is just kind of begin tallying how many electrons we have. When I look up on our periodic table, carbon of course lives in group 4A, will contribute 4 electrons to this particular structure. Oxygen, who lives in group 6A, has 6 valence electrons. I see that there's 2 of them in that formula. It will contribute a total of 12 electrons. So by the time I'm done, I better account for 16 electrons in our structure. Thinking about carbon dioxide and building the molecule, think symmetry. Carbon will become the central atom, and I'm going to build back the oxygens around it. Carbon, who lives in group 4A, I place 1 dot around each side first. The carbon will have 4 valence electrons. I unpartner that s orbital and create 4 bonding spots for the carbon. I'm going to place an oxygen around each side. Again, spread them out. I don't want to crowd the atom, so I'm not going to create these right angles. I could do top, bottom. I could do left or right, but I would not pick kitty corner. It just crowds the molecule. Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Connect a line here for our first bond. 1, 2, 3, 4, 5, 6. Connect a dot here. There's a second bond. We're not done yet, knowing that we have to achieve a stable octet. We can see them coming up to the center to form a double bond in one direction, coming down in the center here to form a double bond in the next. So we end up with carbon, double bond oxygen, 2 lone pairs. Double bond oxygen, 2 lone pairs is our structure for the compound called carbon dioxide, CO2. Let's try a polyatomic ion. Let's try building sulfite. And I'm just randomly selecting to give us some practice. SO3 minus 2. Sulfite, polyatomic ion. Again, just tabulating how many electrons we have total. Sulfur lives in group 6A. It will contribute 6 electrons. Oxygen also lives in group 6A. There's 3 of them there, so that's 18 more. We get to add 2 extra electrons because of the minus 2 charge, so add in 2 more. So right now, we have 26 electrons to place. Sulfite carrying a minus 2, those extra 2 dots. Thinking symmetry, sulfur with its 6 valence electrons. 1, 2, 3, 4, 5, 6 open spots. If I place an oxygen, top, bottom, and right, again I have 3 oxygens to place. I can put the shell around the oxygen and complete its octet. 2, 4, 6, 8, 2, 4, 6, 8. Those 2 extra electrons, I can create a lone pair on the sulfur and a single bond in each direction for the oxygen. This is an ion, so you'll see that written in a bracket carrying a minus 2 charge. The sulfite polyatomic ion has 2 extra electrons based on charge, minus 2. Here's a slide that you can use to check yours as you were building your structures. I asked you to pause the video and just practice. Take a look at how close you came to the structure. Carbon dioxide we drew together. SeOF2 looks like the following. Selenium was placed in the center. Oxygen was built off of it. Now selenium with its Se lives in the same family as oxygen. Se placed in the center, remember it's the least electronegative. So if I had to decide what atom to place in the center, go back to the electronegativity table and find the least electronegative and make that the center atom. So since selenium and oxygen, I had just one of each of those, I had to decide which one to place in the center. Selenium has a smaller electronegativity value, therefore I knew to place it there. Selenium, of course, had the 6 valence electrons, and I just built around the fluorines and attached the oxygen. Here's a situation, H3PO4, where phosphorus is placed in the center. 4 of those oxygens, again, thinking symmetry, 4 oxygens around the center atom. Remember in oxyacids, and that's what this structure is, oxyacids always place the hydrogen off of an oxygen. Never attach the hydrogen back to the central atom in an oxyacid. So the note to self here, hydrogens must attach to oxygens. This compound has a name. Polyatomic here is called phosphate. 8 turns to ic, and you would hear this called phosphoric acid. Phosphorus in the center, 4 oxygens around, attach the 3 hydrogens to fill those holes. P2H4 might have been unique with its 14 electrons because we don't really have one central atom. We knew to connect the 2 phosphors together and placing the hydrogens to create a symmetrical molecule. So attaching the P's creates 1 lone pair on each of those phosphors and 2 hydrogens off of each. This is the best looking symmetrical molecule where hydrogens were used to attach back to the phosphorus. In nitrite polyatomic ion, nitrogen was placed in the center. We ended with a double bond in one direction and a single bond in the other. Again, with that extra electron based on the charge, NO2 minus 1, we had a total of 18 dots to place, giving us a double bond in one way and a single bond in the other. The next step of our lesson takes a look at how to recognize what are called formal charges. Let's be sure. Let me back up a slide. I think I missed one to slide 50. Sorry about that. The term formal charge says during bonding, atoms may end with more or fewer electrons than the valence electrons they brought in order to fulfill octets. In other words, the number of dots around a symbol may or may not match the group number that it was found in. So I know how many valence electrons for those representative elements by what group number it is. If I start moving around electrons to create double bonds, it may or may not match the group number by the time we're done bonding. And it results in those atoms having what's called a formal charge. Formal charge will have an abbreviation FC for formal charge. Just like you see in the text electronegativity values from our chart, EN, electronegativity values. When you see this abbreviation, it's standing for the formal charge. And it really is just a little formula. We take the valence electrons. The valence electrons come from what group number they're in, group number. From that, we're going to subtract the non-bonding electrons. We often call those lone pairs. Each one of the electrons gets subtracted from the group number. Anything not bonded counts alone. And if I do have electrons bonded, I take half of the bonding electrons. In other words, if I have a bond, let's say between element X to element X, if this is a single bond, I'm going to give one of those electrons to the first and the second electron to the other element. So each atom will take 1 electron in the formal charge calculation. Left OFC. So let's take a peek at what this is saying. The left side of oxygen's formal charge. Alrighty. So for instance, let me find what slide, back up to 49. We were looking at formal charges in this example. Oh, this is what the sulfur dioxide molecule. All right, so if I think about what this structure is, we're going to look at formal charge looking at this picture. But friends, let me just write that a little bit bigger so I just like to get an idea of what the picture is. Alrighty, so we have a single bond going to the right. We have a double bond going to the left. We have one lone pair on the sulfur.